All right. Once again, I'm going to use Excel to solve a lysimeter problem. This is the second problem, and it's a little bit more difficult than the first because it involves unit conversions, and we're using actually English units here. Well, actually, a combination of English units and metric units. So we'll have to use Excel's convert function to make this easier, and this is actually one of the reasons I'm using Excel. So I've written the whole problem. I've copied the problem as written on the right hand side, and now we'll actually go ahead and just solve the entire thing in Excel. So let's actually start by this is the way I like to start. So, we know that it's a cylindrical lysimeter with a radius in feet of 6.5. Right? It's going to list this. Let's just give it one more. Oops. There, 6.50 feet. We can quickly calculate the area. We're going to need that, so we might as well calculate right away. So the area in feet squared, the formula is pi r squared. So in Excel, I say equals pi, and then I have to open and close the parentheses. I don't know why. That's the number pi times the radius squared. Well, the radius is in cell B1. Oops, I can't type at all. 1 squared. There it is. So it's 132 square feet. And let's see the other things. We can start here with the mass. The mass, I'll just say it, mass 1 at the beginning of the experiment was 51,914.5 kilograms. At the end, I'll just call that M2 in kilograms. We had 51,848.8 kilograms. And so the change in storage in terms of kilograms will equal the end weight minus the beginning weight. So that's equal to B5 minus B4. And that was 65. It lost 65.7 kilograms. And remember, to convert that change in storage in terms of mass to a change in storage in terms of volume, we simply divide by the density, which is 1,000 kilograms per cubic meters. So the density, the change in storage in terms of cubic meters of water will equal that change in storage in terms of mass in B6 divided by the density of water, which is 1,000 kilograms per cubic meter. And there you go. So the change in storage is negative 0.00657 cubic meters. All right, so remember, let's just write this down so that we can remember it here, that for our lysimeter, we can write an equation. We'll do it in black here. The storage equation looks like this. We know that I'll write it over here, that the change in storage is equal to the inputs, which is precipitation, minus the outputs, which include drainage. Well, drainage, right? We always have some water draining out. And then the other output is ET, and that's what we want to solve for. That's the thing we want to use the lysimeter to measure. So solving this equation for ET, I get that the ET that I want to measure is equal to the precipitation minus the drainage minus the change in storage. So I'm going to need to calculate the precipitation, total precipitation in some unit, consistent unit, the amount of water drained in the same unit, and the change in storage in the same unit. So we've already calculated the change in storage here as 0.00657 cubic meters, right? And I should probably write this here. This is actually meters, and this is over 10 days, right? Let me just put in parentheses, over 10 days. So this is actually a rate, which is cubic meters per 10 days. This was a 10-day experiment. And I'm going to do this all in cubic feet because the precipitation is given in inches per day and the drainage is given in cubic feet per day. So I'm going to do everything in cubic feet. So I'm going to need to convert this change in storage in cubic meters to, actually, let's just call this meters cubed per 10 days, right? That's what it is. It's over 10-day period. So I want to convert this to feet cubed per 10 days. I should maybe have put all that's the change in storage in kilograms per 10 days, right? There we go. Okay, so we want to convert that negative 0.00657 cubic meters per 10 days to cubic feet per 10 days. And I'm going to use Excel's convert function. If you haven't seen this, this is the coolest thing ever. So I'm just going to say equal convert. That's the function. And there are three arguments. The first is what is the number you want to convert, and that's the number found in B7. And then the second two arguments are in quotes, and they are the units that they're in, and then the units that you want it to convert it to. So these are in right now in units of meters cubed, and I can actually use the exponent sign here. Cubic meters to, that's what they are in, to, I want to convert them from cubic meters to cubic feet. There we go. And it turns out to be negative 2.32 cubic feet over 10 days. All right. Next thing I need to do, so I've got that. I've got the change in storage in cubic feet per 10 days. I need to calculate the change, the additions due to precipitation during that time and the withdrawals due to drainage during that time. So here are my data, and basically I'm going to recreate those so that I can sum them up. So let me show you how I would do that quickly here. So precipitation here in inches per day. Well, actually, let's just do it this way. These are my days. All right, we have day 1, 2, 3, and if I just grab hold of these, see that, and put my cursor on the bottom right-hand corner, this will extend that same series up to 10. There we go. And my precipitation was, I'm just going to copy these numbers, 0, 0.21, 0.51. Okay, there we go. And let's just write all my data here. The drainage in feet cubed per day was 0.8. Okay, there we go. So let me slide over a little bit so I can show what I'm going to do. So I'm just going to sum these up. The sum over all 10 days, right? So this is going to be equal to the sum, our function here, and we're just going to all that. I'm going to sum up all that. There it is, and I can copy that formula. So there we are. So just make sure we know what the units are here. So I'm just going to put this in parentheses just to make sure. These are inches per, now they're inches per 10 day, right? That sum is the total inches in 10 days. And this is the total number of feet cubed per 10 days. So this is actually what we want already. This 7, I'm just going to highlight this number here. That's something we actually, that's one of the numbers we want. We also, this was my other number we want. That's the storage change over 10 days in terms of cubic feet per 10 days. This is the drainage term over 10 days. Okay. This, however, the one above it is inches per 10 days, and we need cubic feet. So remember how we're going to do it. This is a flux, and we're going to need to multiply the flux times the area, which is, again, I calculated it up here, right? This was my area. So I need to calculate. I'm going to have to, you know what, make this easier. I just move that all over to the left so that I don't have to keep moving around to show everything. So remember that this is inches per 10 days. So we just need to convert this into cubic feet per 10 day. So first thing, I'm going to change the units here. I'm just going to change this. So 1.54 inches per 12. Let's just write it over here. Let's just do it right. Let's just do it over there. So P over 10 in inches per 10 days was 1.54, right? And so P in feet per 10 days, that's just equal to the inches divided by 12. So it's just equal to B11 divided by 12. Okay, there we have feet per 10 day. And now if I want the volumetric flow rate, I multiply the flux times the area. So I'm going to take, yes, I want feet cubed per 10 days. I'm going to take the volumetric, I'm sorry, the flux, this here, the 0.128 feet per 10 days, and multiply that by the area, which is above in yellow. So that's equal to B12, that's the flux, times the area, B2. And there you go. It's about 17 cubic feet per 10 day. That is the term due to, what was that, precipitation. So there you go. So, where was the unit there? Okay, there we go. So these are the three terms I needed. Remember over here, let me just remind you that over here I had, this was my equation I want to use, and so I have precipitation, there it is, and I have drainage, that was over here, and I have the change in storage over here. And I'm just going to plug into that equation to calculate the ET. And remember, it's going to be in cubic feet per 10 days. So that's going to equal precipitation, which was in B13, minus the drainage, which is going to be in L18, minus the change in storage, which is in cell B8. There you go. And I get an ET of 11, about 11 and a half cubic feet per 10 days. And now, only thing I have left to do really is to convert that to the average, average ET rate in inches per day. So that's just a little bit of, notice I'm going to want it in a flux. It's in a volumetric flow rate. So let's first, actually, let's just calculate the ET in feet cubed per day. So that would just be divided by 10, right? So that's equal to B20 divided by 10. Okay, there we go. And now I'm sorry, that's not a flux. That is a volumetric flow rate in cubic feet per day. If I want the flux, I divide by the area. So if I the ET in terms of feet per day, I'm going to take my volumetric flow rate and divide by the area. So that's B21 divided by the area. That's the cell in yellow above, B2. And there we go. That's my volumetric. I'm sorry, that's my flux in feet per day. That's one of the things I want, except I want it in inches per day. So the only thing I need to do here now is to convert feet to inches by dividing by 12. So that's equal to, I'm sorry, multiplying by 12. There are 12 inches in a foot. So I simply multiply my flux in feet per day in B22 times 12. And I end up with, final answer here, that my average evapotranspiration over that period of time, over this 10-day period, was about 0.01 inches per day. I should probably express that, oops, wrong way, as just two significant figures. So 0.10, a tenth of an inch per day is the average ET rate based on the measurements from this lysimeter.